In this video, we will encounter another application in cQASM. This time, we will go over how to implement the quantum Fourier transform, which is an essential ingredient in many quantum applications, such as Shor's algorithm. First, we will cover the integer basis state notation that we will use, followed by an introduction to the quantum Fourier transform, and finally, how to implement this on cQASM. Now, we know that any single qubit state can be represented as a superposition of two states. Here again, we use the 0 and 1 states as our basis states, with the normalization condition which imposes that the sum of the squared magnitudes of the coefficients must equal 1. Following this notation, we can represent a 2-qubit state in the following way, where the full 2-qubit state is represented as the tensor product of two single-qubit states. Expanding out the product, we can see how to realize a full 2-qubit state as a superposition over all combinations of basis states. For 2 qubits, we have 4 such basis states, which we can see here are equivalent to the 00, 01, 10, and 11 states. For an n-qubit state, we can follow the same process to represent the full state as a superposition over 2 to the n basis states. We use the variable zi here to represent a unique binary string of length n, and ci are the respective coefficients which must satisfy the normalization condition. Now, for the purposes of this video, we will switch to the integer representation of the basis states. So instead of using a binary string, we will use the positive integer corresponding to that binary string. For example, if we consider a 3-qubit superposition state as follows, here we're considering an equal superposition of the 0, 1, 0 and the 1, 1, 1 state, we can simply convert the binary strings to their respective integers to represent this state as an equal superposition of the 2 and the 8th state instead. This is done purely to simplify the mathematical notation for the quantum Fourier transform, which we will see in a couple of slides. Now, the quantum Fourier transform, or the QFT, is essentially the quantum analog to the discrete Fourier transform. The Fourier transform is a mathematical function that takes some signal in the time domain as an input and outputs the same signal in the frequency domain. We can see some examples in the image here on the right. The QFT will take an n-qubit state as input, and it will detect any frequencies existing within the coefficients of this state. It has been proved that the QFT can be implemented efficiently on a quantum computer and achieves a speedup over its classical counterpart in terms of the number of gates required to execute it. There are many quantum algorithms that utilize the capabilities of the QFT. Here, in this slide, we present the mathematical formulation of the QFT as some unitary operator Q. The QFT will take some integer basis state x as input and output a superposition state over all possible 2 to the n basis states with coefficients omega n, where omega n is given by this expression below. Here we present the QFT in matrix form for n equal to 2, 3, and 4. Note that we can technically define a QFT over all possible positive integers n. However, for the purposes of implementing it on a quantum computer, we will only consider the case when n is equal to 2 to the power of small n, i.e. just some power of 2. On this slide, we present the QFT in Sickert form, and we will see what gates are required to implement it. If we look at the first qubit, we see that first we apply a Hadamard gate. Then we apply n-1 instances of a specific controlled phase rotation gate. This definition of the RK gate is provided on the right, where the subscript k corresponds to the amount of phase the rotation induces. So we apply an R2 gate controlled on the second qubit, then an R3 gate controlled on the third qubit, and so on until we apply an Rn gate controlled on the nth qubit. Then we move on to the second qubit, where again we first start off with a Hadamard gate, followed by an R2 gate controlled on the third qubit, then an R3 gate controlled on the fourth qubit, and so on. We repeat this block of Hadamard and controlled phase gates until we reach the final qubit, where we simply apply a Hadamard gate. Now, we will move on to implementing this on cQASM. As we saw just now, we require two operations to implement the QFT. The first is a Hadamard gate as defined here. For this gate, we only need to specify the qubit which the gate is acting on. The second gate we require is the specific controlled phase gate, also called the CRK gate, which cQASM conveniently has implemented. For this gate, we need to specify the target qubit, the control qubit, and the subscript k, which determines the phase rotation by an angle of pi/2 to the power of k. Now, we will combine everything together to see how we can implement the QFT algorithm with cQASM. First, we must specify the number of qubits. In this case, we will use 4 and initialize all of them. Here, I created a subcircuit for this portion of the circuit. Then we will perform the first block of gates, which again I will create a subcircuit called QFT1. We start off with a Hadamard on the first qubit. Then we perform a CRK gate with the second qubit as the control, the first qubit as the target, and specifying Rk to be equal to 2. We repeat the process for 2 more CRK gates, taking care to specify the correct target and control qubits and the subscript k. We can see the corresponding generated circuit on the right-hand side. Next, we move on to the second block of gates, where again I create a new subcircuit. We write down the specified gates as before. We repeat this process again for the final 2 qubits. And finally, we have created the full quantum circuit to implement a 4-qubit QFT. We took advantage of the gate sets implementable on cQASM to do this in an efficient manner, and this process can easily be extrapolated to larger numbers of qubits. In conclusion, we have covered the mathematical and circuit definition of the QFT, and used the native gate implementations on cQASM to create a quantum circuit that enacts the 4-qubit quantum Fourier transform. I hope you found this video useful in helping you to learn how to write applications on cQASM.